Evening, ladies and gentlemen, and welcome to Muni Night here at the Strand Theater. My name is Seth Prentice, Community Marketing Manager for Armstrong, and also host of the Armstrong in the Loop podcast, found on all major podcast platforms. Tonight, we would like to thank our sponsors, Adams Township, for initiating this innovative ecological approach to stormwater management, the Adams Township Supervisors by name, which is Russ Ford, Ron Chanela, Linda Lease, Ed Vogel, and Clayton Mora. Armstrong for recording this evening and rebroadcasting it on the Armstrong Local Programming Channel, also now named the Armstrong Neighborhood Channel. Chatham University and Dr. Weitzel for explaining riparian plantings to us and their effect on slowing stormwater. Deep Well Services for renting the Strand tonight. First Energy for notifying Butler County authorities that this informative evening is being held here at the Strand. Also, thank you to the Strand Theater for hosting us tonight. Olson Crass Associates, Ron Olson and Phil Gruskevich for explaining their proposed MS4 project on the Breakneck Creek. And last but not least, Zelienople Area Business Association for initiating this pilot program of 4th and 5th Thursday municipal nights at the Strand. Municipal nights are on the evening of informal presentations of what local municipalities and authorities are doing to their constituents. Fourth Thursdays are Zaba's way of giving area residents an overview of issues that affect everyone in our area, like residential developments, parks and recreation, emergency management, traffic, and of course, stormwater. Please encourage your municipal to conduct a very public and informal forum here at the Strand Theater. The schedule for 2020 is being prepared now. Our speakers this evening will be Phil Gruskevich, Project Manager of Olson Craft Associates, and Dr. Roy Weitzel, Aquatic Laboratory Director for Chatham University. Gentlemen, welcome to the stage, Dr. Weitzel and Phil Gruskevich.
Check. There we go. Okay, great. My name is Dr. Roy Weitzel. I'm coming to you from Chatham University. Interestingly, Breakneck Watershed starts on our campus up in Gibsonia and flows down, of course, to the Connoquenessing. I also live within the watershed in Mars, and so I've got a vested interest in this effort and thinking about the health of the watershed overall. I'm going to apologize in advance. I got hit earlier this week with the flu, and I'm still recovering, and so my voice is pretty weak. Thankfully, I've got the microphone, and I'll try not to cough into the microphone. Hopefully, I can make it through without too many issues. We've come to this project pretty recently, but I was asked tonight to come and talk about riparian areas, what they are, their structure, how they function, and what types of goods and services that we get from them. They're incredibly important parts of our ecosystems. We rely on them quite heavily. They are also probably one of the most abused parts of our ecosystem during the process of urban development. And so we really need to come to understand them, to figure out and try to quantify what it is that we lose when we impact them, and how we can move forward with development in the watershed in a sensible way, not being anti-business, anti-development, understanding that the watershed is going to develop, but trying to figure out how to allow that development while not losing the critical services that we get from these habitats. So I'm not going to spend a lot of time, but this is really an ideal picture for me of what a stream and its riparian zone look like. We've got a nice naturally meandering stream, vegetation all the way down to the shoreline, no obvious signs of excess siltation or erosion, and a nice tree canopy, very idyllic and for all intents and purposes, a perfect stream scenario. Now, this is what things look like before we start developing, right? And what every action that we have has an equal reaction from the system, and we want to make sure that we can preserve these functions and move forward as we develop the watershed. This is from Wolf Creek, just up near Slippery Rock. So not too different from where we are right here. Looks like my slides are getting cut off a little bit, which that happens. I'll try to cover for that informational loss. This slide, I guess, am I going to need to say, next slide, please? Sure. Okay. Go ahead and filter through, hit it once, keep going. This is just sort of my biography so that you know that I'm not just some guy off the street. That's good. But I do work at Chatham University. I run the aquaculture laboratory there. We also work in natural stream systems off campus. I've had a long career working with aquatic resources and with various entities, mostly with fish and centering around fish habitat, community health, and that type of thing. But most recently, I did my PhD at University of Maryland and graduated in 2015. And my project was focused on urban systems, so urban stream systems, how we develop watersheds for human development and the effects that that has on the functions and the communities that those ecosystems give us. And so this is kind of right in my wheelhouse. And I'm really excited to work on this project with the Township and with Olson Craft and the other partners. Next. Maybe. So, yep, there we go. What is a riparian zone? I'm a riparian. What does that mean? Very quickly, I did a Google search, just trying to get the basic information to show you. Relating to or situated on the banks of the river, relating to wetlands adjacent to rivers and streams. We're talking about the areas of transition between the upland landscape, dry forests and natural areas, and the very, very wetlands, rivers and streams that we have around here. It has a Latin root, basically meaning bank. All right, next. Yeah, I'm going to lose a lot of information on the bottom of these slides, but that's okay. There's too much in here already. If we look at a more formal definition of what is a riparian ecosystem, I looked to the American Fisheries Society and some of their publications. A riparian ecosystem is all of the complex assemblages of organisms and their environment that exist adjacent to and near flowing water. And I would extend that definition to include the flowing water itself, because there are lots of processes that happen in these areas that tie the stream and the upland landscape together very tightly. And down below, we were looking at a picture. We've lost most of the bottom, but it includes the stream itself up into the bank edges where the vegetation begins, and all the way up into a certain area of the uplands. And this area between the edge of the bank and where it extends up into the uplands is going to be highly variable depending on the status of the environment and how much precipitation and groundwater contact there is. The important thing is that there is a water contact in the soil between the stream and these upland areas that serves as the substrate for many, many of these important ecological functions that I'm going to talk about. Next, please. So there was a fellow named Ewing back in the late 70s who came up with two essential characteristics of riparian ecosystems. First, that there's this laterally flowing water. So if you think of a stream and its course through the landscape, it's linear mostly, right? It's flowing from point A to point B in a roughly linear fashion. But the riparian ecosystem that's alongside that is governed by laterally flowing water, water flowing outward from the stream channel that rises and falls at least once within a growing season. And this is an older definition where back some time ago, the water may really go laterally only once in a season. What we're seeing now is that with increased rainfall and increased surface runoff, that we're having more than once a season that these streams are trying to get up and out of their banks to handle all that water, and in many cases it just can't happen. The important thing is that there's an incredible amount of connectedness between the stream itself and these lateral ecosystems beyond the stream edge, and it's not a finite boundary. It changes seasonally, it changes up and down the stream. It has a lot to do with many factors: topography, microtopography, the presence of wetlands and other things like that. And so the picture at the bottom is really, this is a picture from a restoration plan showing the multiple uses of the floodplain and how everything is connected. And you can see that it's not just the river stream itself that represents the riparian zone, but everything out to the floodplain boundary and even a little bit beyond that can be considered riparian. Next. So again, what is a riparian area? It's the interface between the land and a water body. It doesn't have to be a stream, but we're talking about a stream tonight. It's transitional, okay? So it's neither dry or wet. It's semi-terrestrial, meaning that it's sort of like the land, but it's governed by water. And we call these kind of areas, these transitional areas between ecosystems, dry, upland versus stream, or any two ecosystems really, an ecotone. And I'll go more into what that means. I tried not to be too jargon heavy tonight, but it's really hard, right? These slides are coming from the classes that I teach to my students, and we're talking about these things in depth. And I'm trying to give you an overview, but I can't get rid of all the terms. So I apologize, and if you don't understand something, maybe in the question and answer session we can go back and visit what some of these things mean in more detail. Can you go back one, please? Thank you. The riparian area extends from the edge, question mark, of a water body to the edges of what we call upland communities, those that are not driven by water and water flow. Okay, and I put a question mark there because there is no boundary, black and white, right? It's a fuzzy boundary that moves constantly, depending on what we're doing with the landscape and the seasonality and how much precipitation we're having. The important thing is that this zone is incredibly important for these interactions that are happening between the two ecosystems. They're integrated very tightly together, and therefore there's a lot of functions that are going on there that we rely on for what I'll call ecosystem services, and we'll talk more about what that means later. The important thing to remember is they are not static. It's not black and white. They're not fixed on any point of the landscape. These are very dynamic environments. They're changing all the time. Strong energy regimes, lots of different types of habitats, and a diversity of ecological processes that are happening that we rely on very tightly. Because there are multiple ecosystems and lots of processes coming together, these areas tend to be locations of strong, high biodiversity, right? So you might have a certain number of species of plants and animals that live in the upland landscape and those that live in the stream entirely, but where these two come together is a perfect place for many of those species, and so they're very important when you're talking about issues of biodiversity, wildlife and plant health and function. Next. So this term ecotone, and this is I like this graphic because it sort of captures all of what I just said, right? You've got your land ecosystem on the left, you've got your aquatic ecosystem on the right, and you've got organisms there that are adapted to live and ecological processes that are happening in each of those ecosystems. And then you've got this weird thing in the middle, right? Governed by the presence of water, where there are other organisms that are adapted to live in those places, and very important processes that are happening in that transition that we, if we can, as we develop, we don't want to compromise. We rely on them very heavily. Next. Please. Okay, so I am going to be somewhat repetitive, but I'm just trying to build on these concepts. Riparian areas are not just, it's just not one place or these isolated spots within an area, okay, an area that we might call a watershed, right? They form networks within the catchments, because if you think of the way that streams meander through the landscape, the way they come together, there is a riparian zone along every inch of every stream and beyond in the landscape, and they form these networks that are connected through process and through movement of organisms and materials, right? They extend into the water and into the upland landscape, and there is not a finite zone. When I talk about connectivity, I'm talking about not just biological organisms moving back and forth, but physical and chemical processes that are happening that are really critical to the ecosystems. Again, repetitive, but I'm trying to nail some things down here. So where these areas are within the landscape is critical to the overall ecosystem function, okay, and the levels and quality of the goods and services that we as humans rely on and can expect to get from these ecosystems. We are dependent on them. Next. Don't worry about all the words. Look at the picture, the blob, the green blob up there with all the numbers, and don't worry about the numbers either. But that is a hypothetical watershed, right? We've got very small headwater streams indicated by those low numbers, and as the numbers increase, those streams are getting larger and larger as they come together until they all flow together and come down into one discharge point. Think about the mouth of the Breakneck Creek as it enters the Connoquenessing, right? We talk about stream order because it gives us a way, and we number these things, it gives us a way to understand where we are in the watershed and what we might expect to see. One of the most important things to get from this diagram is that greater than 80% of the length of any stream system in the North America or even globally is consisting of these very, very small, thin streams that don't seem like much each and of themselves, but when you think about it, they constitute most of the water in a watershed. And it's these very streams, these ones and twos, and in some cases the threes, that are the ones that are most impacted by development. They tend to be on the flattest landscape. They tend to be very small. Some of them don't run continuously all year, and therefore we don't, many of us, don't really appreciate the impact of their function and how much we rely on them. The other thing to take away from this is the idea that riparian ecosystems change in width and function from top to bottom of a watershed. Headwater streams, the small ones, have a much more intimate relationship with the landscape because more of their area is in touch with the soil and the plants and the other things. And this is where most of the beneficial functions of the watershed are occurring, by and large. Once you get down to, you know, a third and fourth order stream, you're talking about a pretty large body of water where there's relatively very little contact with the landscape, and that water is basically moving through like a conduit, except in high water situations where there's flooding, which is a natural function but has also become much of a curse for us in the lower parts of this watershed anyway. Next. Think about these networks of streams like the alveoli in your lungs, right? Each one is extremely small, but if you start losing lots of them, you're taking away very rapidly the function of your lungs. And it's the same way with a stream on the landscape. Picture this lobe on the left. You can see the stream running through it, and it's in intimate contact with all of that landscape. You start taking those little branches away, and pretty soon your lung is gone. And unfortunately, that's basically the way it works when we start to develop stream networks. We start at the top where the smallest streams are, and we end up moving downstream. And it isn't too long until the function of the entire system is compromised, and we have to start dealing with issues of sedimentation, flooding, and loss of biodiversity, and these other functions that we're so reliant upon. Next. Connectivity with these ecosystems and the landscape is critically important. I've already said that. If you look at the left and you see a stream, a hypothetical stream flowing from the bottom to the top, or from the top to the bottom, either way, I don't know which way it's going. In a connected landscape, you've got materials and organisms and water and goods and services, therefore, moving up and downstream, back and forth through a connected landscape. You start losing some of that connectivity, burying those streams in pipes, paving them over, filling them for agricultural work or to build a new development, and you start losing connectivity, and therefore you start seeing that the organisms and the processes that are happening in what's left are isolated and not connected to the mainstream of the channel, and that's a big issue. Next, please. Just as an example, something that you might take home with you, this is not from around here, but the interconnectedness of streams and their riparian zones. In Alaska and northern alpine regions, right, there's a very intimate relationship between the salmon that live in streams and the organisms like bears, eagles, and plants that live up in the uplands outside the streams. Every year, at least some of the salmon come back, and they swim upstream, and they spawn and they die, and they serve as an incredible nutrient source for bears and eagles. And bears and eagles will take these fish up into the riparian zones adjacent to the streams, and they'll eat parts of them, the juicy parts, basically the fat and the brains and the things that give them the most energy, and they leave the rest to rot. Those nutrients then, which are based in the sea, right, are up in these upland freshwater habitats. They dissolve and are absorbed into the landscape and are taken up by plants. And these orange critters on the right there that look sort of like raspberries are called salmon berries, close relative. And what they found is through doing the science to trace these nutrients as they move through the landscape is that these riparian areas and the salmon berries in particular are solely dependent on the marine nutrients that are coming in through the salmon. You lose the riparian zone or you lose the salmon, and those berries are not going to be found in those areas. And so that just trying to show the interconnectedness. Go ahead, next one. This is one a little bit closer to home, the red-spotted newt. Has anybody seen these bright orange guys walking around in the forests under your feet? They're orange for a purpose because they're toxic and you don't want to eat them. They're saying, hey, you don't want to eat me, right? But that's only one stage. That terrestrial stage of that organism actually starts in a pond or a river or stream as a fully aquatic salamander. They mate, they lay their eggs, the eggs hatch out. The eggs are in the larval stage for a few months, and then they move onto the land, sort of their teenage years, right? And they're going out and they're eating insects and they're getting all that terrestrial nutrients. And then when it comes time to reproduce, they move back to the water. They take those nutrients and their bodies with them. They put those nutrients into the eggs that are going to serve for the next generation, and the whole life cycle starts again. If you don't have a high quality aquatic and upland terrestrial habitat and the riparian zone in between. You're going to break this life cycle. And it might seem like an inconsequential little creature, but it's just one example of many life cycles for organisms that begin and end across that transitional zone. Next, please. Sorry, I'm going to get a sip of water while I can. So how wide is the riparian zone? Well, I've already said that it's variable, right? It changes all the time, depending on the landscape, depending on the season. And the problem is that we try, as we develop watersheds, to impose a standard buffer width, a standard riparian width that we will preserve as we develop. And it doesn't always match up with reality, right? Sometimes it may be less. 50 feet might be great. 50 feet is only a recommendation. There is no requirement for a 50-foot buffer zone, to my knowledge. But it depends on many factors. The topography, is it steep? Is it flat? What is the local water regime? How much precipitation do we get? How is it spread out seasonally? What are our soils like? How close are the roads and other man-made structures and land uses like agriculture and urban development? All the interactions of all these factors work together to determine the width of a riparian zone, and there is no definite answer, right? Like I said, most state and local regulations specify a standard buffer width, and it doesn't match up with reality. So what are we to do? It's a good question, and I don't have an answer necessarily. Next. Most of the time, people that have studied this thing have talked about really the ideal buffer width for a riparian zone to try to maintain fully the function of these areas is maybe about 30 meters. That's almost 100 feet. I would say that in many cases, depending on the topography and the situation, that isn't enough. Sometimes it's more than enough. But if you think most of the developers that are coming in now are, the suggested width is about 50 feet. That's half of what the scientists that studies these things are recommending. And so we're immediately basically cutting off half of the zone in which we rely on nominally to support these ecosystems. So this is a graph from a paper talking about how do we move forward with riparian zones and trying to use landowner incentives to protect these riparian critical areas. And so the larger the riparian width, the more incentive to the landowner, and that oftentimes comes in terms of money. And 30 meters was about the minimum that people settled on to preserve all of these functions, and subsurface flow, groundwater flow, temperature control of water that's going into the streams, sediment removal, and nitrate removal, all these things that we rely on that I'll get into more detail briefly. Next. All right, I threw this one in at the last minute, and I won't spend a lot of time on this, but I wanted to re-emphasize that the width of the riparian zone is dependent on many, many things. Changes in elevation, small changes in topography within that zone. We don't have to worry about tidal influence here, right? The oceans are pretty far away. But then there's the quality of the water and the soil and the gradients that exist. And just to give you an idea of sort of some of the diagrams that we use to talk about zonation of riparian zones, and we usually base that on the vegetation, and not just the vegetation, but the reliance on water or their acceptance of having wet feet, right? Next. This one I threw in the last minute also, and I just want to use this as an example of we're not just talking about a thin strip of land next to a stream, right? The riparian zone by function will include the entire floodplain of the stream if it has one, and all of the structures that exist on that floodplain. There might be wetlands, springs, terraces that are slightly higher, that are coming from from sediments that have been deposited in the past, different islands and braided chains and et cetera. And it isn't until you get up into what we call the hill slope, which is where the topography starts to rise fairly steeply, that you get out of these areas. And so, again, if you were just to come into where the stream is on this side, on the right, and just do a 50-foot buffer on the side of the springs, you'd be adding absolutely no protection to all of this function that's happening in the floodplain. And really, that's why we're here. We're talking about this floodplain project that's going to be going on, hopefully, that we're moving forward on to reestablish the connectivity between the streams and the floodplain and reconnect and reestablish all of that functionality that has been lost through the urbanization effects on the stream so far. Next. The streams exist for a reason. It's not necessarily to support us as humans and our civilization, right? But there are many services that we get from streams that we rely on and that most people don't think about. They can be divided into various categories. This is adapted from a United Nations publication called the Millennium Ecosystem Assessment, which was an assessment of the status of global ecosystems. And for freshwater, these are the 4 main categories that the systems come in. Let's start over on the top right, provisioning. These are products that we get from aquatic ecosystems. And really this is applying to any ecosystems, but I'm mostly thinking about aquatics here, right? Food, raw materials, medicinal resources, and fresh water. Hopefully clean, pollutant-free. Not the easiest thing to find around here these days, but we have a long legacy of issues that have left us, or of land use and use of these resources that have left us with a lot of issues. We have regulating effects, which are the largest category, and things that we really might not think about too much, but that we are definitely talking about here tonight. Water regulation, right? The flows of water. Erosion regulation, right? A certain amount of erosion in a stream is natural, but we've got way too much, and our stream, Breakneck, has been listed as impaired for sediments that are coming from this erosion. Water purification, waste treatment, disease and pest regulation, pollination, etc. This is an important one, moderation of extreme events. As we move forward over time, we are seeing changes in the climate, and whatever the source, the climate is changing, and we are getting more extreme wet weather events than we have had before, where, whereas a 100-year flood used to occur every 100 years, now we're having multiple 100-year floods in just a few year span, right? And so we rely on these natural ecosystems to temper those, and we're losing those ecosystem services as we develop the way that we have. Supporting functions enable the production of all the other services: soil formation, photosynthesis, nutrient cycling. That's a critical one in riparian zones, the nutrient cycling. And then finally, we rely on them for a lot of cultural aspects that many people don't really realize. Recreation, mental and physical health, aesthetic values, and even spiritual and religious values, depending on where you lie upon that spectrum. Next. So getting more boiled down into specifically what we get from riparian zones, hydrology. They regulate water flows. They affect the soil development and the growth of vegetation. Maintenance of base flow. Base flow is a critical thing. The ecosystems that we have here, most of the time, are flowing at or near what we call base flow, which is just the normal water regime that's coming out of the ground or off of the surface. And there's a lot of water storage involved in that, in the groundwater and even the near surface sediments that we have, gravel and sand and the like. Nutrient cycling. Nitrogen and phosphorus coming from a variety of sources have some pretty drastic effects on our ecosystems. And if you think about Lake Erie and the big blue-green algae blooms that they've been having, that is a direct result of excess nutrients bypassing the riparian zones and making it straight into the water and causing issues. We have those same issues in all of our water bodies around here. It's just not quite as obvious most of the time because we don't have the fluorescent bright green algae that kills our dogs and gives us respiratory issues. But energy transfer, organic matter produced by trees in the form of leaves and plants and plant tissue is an important energy source for streams. And when we change the nature of the vegetation in the riparian zones, of course, we change the energy transfer, which goes all the way up the aquatic food chain and affects the sport fish and other things that we like to eat and fish for. Here's the big one for this watershed: attenuation to downstream flooding. Right? A healthy riparian zone is going to absorb most of that water that's falling on the landscape in one way or the other and slowly release it into the stream. When you disconnect a stream from its floodplain and from its riparian zone or eliminate the riparian zone altogether, you lose that attenuation of downstream flows very quickly. Of course, water quality, reduced water velocity gives more contact time with the sediment and the bacteria that are living there that can increase our water quality. Aquatic life goes without saying, and then of course terrestrial life. Although you wouldn't think it, but these things are so interconnected that much of the upland terrestrial life that we know and the organisms that we see as important are relying heavily on these riparian zones for many reasons. Next. Okay. Somebody told me never put a slide on there that has too much information that people can't get to it all in a matter of a few seconds. But I'm not going to go through all this. The complexity of this diagram and all of the lists of the functions and the goods and services that are provided by riparian zones, it's too much for me to go through, right, in a reasonable amount of time. But we need to think about all of these things, both above the ground and the subsurface, and especially the subsurface, and where the water table lies in relation to the stream. This is where a lot of your nutrient transformation, your nitrogen and your phosphorus are going to be bound up in the sediments, transformed by bacteria into something less harmful, or just totally sequestered, period. And it's this intricacy of this connection between the landscape that accounts for all these functions. The depth to groundwater is critically important, and what we'll see with Breakneck Creek in Phil's presentation, I'm sure, and I'll maybe try to speak to it a little bit in a minute, is that as we urbanize, these streams downcut into the landscape and the sediments pile up alongside, and what that does is effectively disconnect the stream from the floodplain, but it also lowers the water table, because the water table is going to be basically where the bottom surface of the stream is. And if the stream's 9 feet down in sediments, then that means that the water table is going to be, much farther down from the surface, and the plants themselves are going to have a harder time reaching that water table to take advantage of the nutrients and play their part in the function of the ecosystem. So when we think about riparian zones, we want to think about the connectivity and the continuity of the buffer corridor. We want to think about how wide that buffer is and whether it's covering all of these functions. The vegetation that lives there is critical, right? We want to see native, adapted, wetland and riparian species there, and what we have seen in a lot of these with the lowering of the water table and disturbance by the streams is a lot of exotic species coming in that have much shallower root structures and just aren't able to take advantage well, they can take advantage of the water that's there, but they're not providing us the services that a native vegetation would do. The wetlands and depressions within the floodplain are key because this is where the water is going to be stored and where that vegetation and the soil biota, the bacteria and things living in the soil are going to be in contact with that water and taking care of all those nutrients. We want a large amount of organic matter in the stream. Our streams around here are naturally forested, meaning the canopy is completely closed, and they're not getting their energy from the sun necessarily. They're getting it from the leaves that fall in it. So if we widen those corridors, take that vegetation away, the nutrients change, the regimes change, the organic matter isn't getting in, and that's what these critters, the bugs and the insects that you're using to catch larger fish are relying on to eat and then transfer that nutrient up the food chain. The last thing I'll say, and this is just in passing, is that large woody debris, trees, sticks, logs, leaf packs, all of this stuff that are in the streams are critically important to the function of those streams. And there are natural amounts of these things that should be in streams. What we find as we develop is that we remove a lot of the woody debris and the leaves and the other organic matter from the streams, either indirectly through taking away the riparian trees and zones and paving and having turf grass all the way up to the edge of the stream, or on purpose because, for instance, in Breakneck Creek, as we are having these flooding issues, there's the impression that having big obstructions in the stream channel is not a good thing because it's holding back the water and creating the flooding. And while there's a little bit of truth to that in an impacted ecosystem, for the most part, having large woody debris, trees, logs, sticks, leaf packs is critical to the function of the ecosystem. And when we remove them, we may not necessarily be addressing the issue, but increasing the problems that we're having. And that could be controversial, but I'm going to stick by that assertion. All right, what do rivers do for us? They do lots of things, right? And the whole purpose of this slide is not the pictures other than the $ up there on the right and the fact that all of the things that we get from these streams in their natural or semi-natural state can be valued in monetary terms, right? So just recently, several years ago now, I have 1997 over there. There's been a revisit to this, but somebody went through and tried to, on a global scale, figure out how much money we're making or saving off of the function of these natural ecosystems. For wetlands, globally, 4,879 trillion. I don't know what what is that? That's like, what's beyond trillion? And then what's beyond that? So 4.9 quintillion dollars globally. What does that mean to us? Well, we're going to see a percentage of that. It's not going to be as impressive, but if you had to pay for it out of your pocket, you'd certainly reconsider, right? 3,231 trillion for floodplains, right? Together, just those two ecosystems, right around 24% of the total annual ecosystem services value on Earth. These are critically important, and we can assign a monetary value to them. Right? Oftentimes that's what it takes before people will start to really consider shortcutting the process and getting rid of these ecosystems. Next. Real quick, I already touched on this. Most of the carbon that drives these systems, stream systems, are coming from leaves around here, right? It's called allochthonous. It means coming from within, or I'm sorry, from outside. The leaves fall in the streams. They are broken down and shredded and eaten and consumed by macro invertebrates and other organisms, bacteria, and then that is transferred up the food chain. So our streams around here are getting most of their energy from the riparian area. So when we take it away, obviously we're making some major changes. The opposite of that is autochthonous, which means from within. When you strip away the riparian zone from a stream, sunlight takes over. And while that's okay, and it does provide some amount of carbon to the system, it's not as high quality. And the organisms that are living in our systems are not evolved to get their energy from that. And you quickly see a decrease in the food chain and the amount of organisms that are living in the system. And this thing about bacterial production, none of this would work. We would not be here as humans if it wasn't for bacteria, beneficial bacteria. And when you start affecting the bacteria that are living in the systems, that's the start of the end. Not to be too doomsday-ish. More talk about coarse woody debris and the importance of leaf packs and all that stuff. It is important, and we shouldn't see it as an obstacle, but as a benefit in a properly functioning ecosystem. Next. How am I on time, by the way? What? Should I just keep talking? Okay. I'm not going to spend a lot of time on this either. I just wanted to give you more of a pictorial representation of the interconnectedness of the system that was more digestible than that massive diagram that I put up before. The important thing in here is on the far right, the leaf fall and the vegetation matter that's falling into the streams that serves as the primary source of energy and carbon for the ecosystem. And then as you can see, it works its way up through the bugs, through the fish and the algae, into the terrestrial invertebrates, the lizards, birds, bats, and spiders, and of course back up into the larger ecosystem and terrestrial with the organisms that then prey on them. So yes, critically important. Next. Just to beat a dead horse, I had to include a figure from my dissertation. As we move from a perfect stream to 100% riparian loss, that's a buried stream over there in a conduit from Baltimore, we see in the literature decreased assimilation of nutrients, sediments, water, decreases in available habitat for organisms, a decrease in connectivity between habitats, which affects their function, and a decrease in the potential for colonization of plants and animals back into a disturbed ecosystem. All of that equates to a loss of ecosystem services, which I hope you understand has a real monetary value. Next. Okay, so really briefly, because it's not my area, I was asked to talk about riparian plantings. And I just don't know, since I'm more of an organismal biologist, fish and bugs, not so many plants, I don't have on the top of my head all of the plants that would be perfect candidates for restoring the vegetation in our riparian zones. What is important is that it's not just one type of plant or another. You have to think about the whole spectrum from inside the water all the way up into the fully dry areas, right? So hydric soils are ones that are governed by the presence or the movement of water, right? And this is really going to be the heart of your riparian zone. Those non-hydric soils might not be recognized as important. It's not a wetland if it doesn't have hydric soils. That doesn't mean that the function isn't there. As I said, the water moves back and forth and up and down seasonally, and so it's not enough to say, okay, we're going to come, to the first, where we get the first, the boundary between a hydric and a non-hydric soil, and we're going to stop there. You really have to have a buffer for your buffer, believe it or not. There are many, many plant lists and many, many resources on the internet for species that are adapted to all of these different zones, and that's something that we hope to work with the other stakeholders to develop an appropriate plant list for this region. They need to be native. Next, please, and I'll show you why. All right, this is a prairie plant root diagram. Well, what does that have to do with us? Well, many of these things that are considered prairie plants from the Midwest are found around here. Different forbs, different grasses, different plants. And what we see is that, you see the plant on the left and the right is a foot scale going from 0 at the soil horizon up to 7 feet or so, and down into the soil some 15 or more feet. All of these native plants, different types of grasses and forbs, so wildflowers and certainly trees and other things like that, are going to have much more well-developed root zones and much deeper into the substrate to break that substrate apart, to allow water infiltration, to reach down to the water table and get those nutrients and water up from down below. Most of the exotic plants that we are seeing major invasions with along our streams, honeysuckle, Japanese barberry, multifloral rose, garlic mustard, etc., have extremely short root zones in terms of inches or maybe a foot, right? And then that little red circle up there on the left is our turf grass. And many people like to see the water that they have in their backyard or whatever, and so they mow all the way down to the water's edge. And they leave a grass buffer, but really the roots of that grass, this is Kentucky bluegrass, but we would have some sort of fescue around here or whatever the Pennsylvania mix is that you buy at Lowe's. You're talking roots that really go down just an inch or two and can very easily be disturbed and washed away, whereas the roots of these native plants are much more developed and hold that soil together and are much more resistant to the erosive forces of the water. Next. Okay. So I've been talking way too long already, and I'm going to try to finish up pretty quick. But let's look at some landscape pictures here. The one on the top is sort of what I would call, besides the bridge and the little bit of development over there, pretty much your ideal riparian landscape, right? Fully forested all the way to the water's edge, very little land use disturbance happening. That's an ideal situation. I don't know where that is. It's somewhere up on the Mississippi or I don't know. But more typical to this region are the three pictures on the bottom, right? We are highly forested historically to the point where there were no trees at one point. And then agriculture came in, and a good amount of our landscape, for better or worse, is still in agriculture. If you're lucky, you've got a very thin riparian zone along there, but there are lots of opportunities for water to bypass that riparian zone and get directly into the stream and taking sediments and nutrients right off the field. This is the big one that we're experiencing now, right? Urbanization in the Breakneck Creek, lots of impervious surfaces. And then, of course, oil and gas mineral development is happening, and while there is a buffer there, there is still quite the opportunity for pollutants and other things to get down into the groundwater and into the water, bypassing the riparian zone in that regard. Next. So, Phil, are you talking much about stormwater and those types of things? Okay, so maybe I'll breeze through this really quickly so that I don't take any more of your time because I've already talked way more than I would like to. Basically, what we're talking about urban development and stormwater is impervious surfaces and increased flows to streams and through and degradation of the riparian zone through the installation of houses and sidewalks and pavement and lawns. Most people don't think their lawn is necessarily a bad thing, but again, very shallow root structure. And with our soils around here, for instance, I live in Orion Homes development, and I'm not trying to talk bad about them, but I observed when they built my house that they took all of the organic topsoil off down to the shale and then brought back in this really substandard clay, stick, rock mix that they called topsoil, and then planted turf grass on top of it. And in that kind of situation, you really have an effectively impervious surface. The water's not going to infiltrate. It's going to go over the land, and it's going to take everything that it can from them. Now, we try to do things on our lot that minimizes the runoff, but it's a matter of fact. So flooding has become a huge issue and contaminated with pollutants. Next. Increased impervious surface basically changes the water budget of a site, and you lose evapotranspiration, which is water going through plants and into the air. You increase your runoff and decrease shallow infiltration and deep infiltration. Shallow infiltration is this organic layer, basically, of topsoil, which really in many places is only 8 or 12 inches thick, but it has a strong organic content. It can absorb and hold that water. The deep infiltration is what's responsible for recharging our aquifers, where we get a lot of our water. And of course, as you increase impervious surface, that changes everything to the point where you're getting very little infiltration and very, very little deep infiltration. And you get lower evapotranspiration, which makes it hotter in the cities and all of that stuff. Impacts can be direct or indirect. Most of what we're going to see in the breakneck is indirect. It's not like we're paving the stream and taking all of that away. It's mostly has to do with high flows that are reaching the stream and causing erosion issues and nutrient issues. Next. More water faster. That's the problem. We need to think about how we manage the landscape and try to hold that water back, give it a place to go and settle down and lose its erosive energy, rather than just shooting downstream and going into people's basements and into the towns. I think I'm going to talk about this urban hydrograph, and then I'm going to stop because I could keep going, but I don't want to take away from Phil, and I definitely want to have some time for questions and answers. But this is basically what we see in a pre- and post-urban world, right? Pre-urban would be yellow, where we have a rainstorm, and over time, we see the discharge increase fairly slowly and then gradually decrease down to a point, and really, that means the landscape's holding the water, it's slowly releasing it. Once we install all this impervious surface, what we tend to see are these really rapid increases in discharge and then a rapid decrease, a flashy stream, which indicates a lot of energy, a lot of erosive force, and water moving very quickly through the landscape and downstream and creating issues downstream. Do me a favor, can you move to the slide view where I can see all the slides on one? You know what I mean? If not, I'll just quit now. Okay, that's okay. The last couple slides that I wanted to show, and again, I apologize for going over time, we're basically talking about, let's not even get into that. How do we manage stormwater? Moving forward, right? We've got to think about a range of solutions. In the past, it's been, and if you can just cycle through these as I'm talking, that's great. It's been with hardscaping, right? Putting things into pipes and channels and trying to get it down away from us as fast as possible, which is great in a sense, but it causes issues to all you folks downstream, right? So as soon as the water leaves my property, I'm happy, but then now you got to deal with it and all the water coming from all these other places. And the way that we want to, and then if you think about the way that it affects the combined sewage infrastructure that we have, and putting human waste into the streams and into people's houses, it's really not good. We're moving away from thinking about hardscaping into green infrastructure, right? And that's sort of what we're going to talk about tonight with Phil and his group, is reconnecting the floodplain and allowing that water to rise up and spread out on the floodplain and stay here. So, whereas we have levees on the sides of our streams, either natural or man-made, that are meant to just channel that water through as fast as possible, we're talking now about, okay, we need to come back from the stream and think about the floodplain and move those levees out and move and establish that connectivity so that the water isn't just shooting through as fast as possible, but comes up and is allowed to go out of its banks onto the floodplains, interact with that vegetation and the topography to steal the energy, the erosive energy out of that water, and to settle the sediments and the pollutants and anything else that's in the water down where it can be sequestered and transformed into something less harmful, or at least kept out of our water system. Another ideal picture, I don't know where that one's from, but it's beautiful. I like the vegetation all the way up to the stream. You don't see any obvious signs of massive erosion. It's peaceful and clear and etc. So thank you very much. I'm sorry I talked so long. I hope that we have plenty of time for you to finish your presentation and then to have some back and forth.
All right, thanks, Dr. Weitzel. My name's Phil Griskevich. I work for Olson Craft Associates. We're an engineering firm in Butler, PA. We're also the municipal engineers for Adams Township, Valencia Borough, and a couple other municipalities in the region. I see Harmony here. Do we have any other municipalities present this evening? Okay, back there. All right, so what I'll do in order to cut down on a little bit of time here is skim over the MS4 program. Our project is part of the PADEP mandated MS4 program, and without that program, quite honestly, we wouldn't be doing this project. So this is a good project. It's a good program. Go ahead and hit the slide for me, please. I just want to touch on a couple quick things to get us all on the same sheet of music, since I know we don't all deal with this kind of verbiage on a daily basis. But the MS4 program, that stands for the Municipal Separate Storm and Sewer System. It was actually started in the 1990s as a federal program, and it's been handed down to states. Larger cities like Pittsburgh, Philadelphia, they've been in this program for years now, and it's just now hitting our smaller municipalities. I'm going to jump down to the BMP. It's the best management practices. All intents and purposes for the MS4 program, a stream restoration project is a BMP. Really, it's just a fancy way of saying it's a feature that is supposed to accomplish a certain goal. Like putting silt socks down is supposed to stop sedimentation from leaving a site. That's a BMP. And then down here, this 100-year storm event. You know, that's kind of a misclaimer that a lot of people maybe misquote or misunderstand. You know, having a 100-year storm event does not mean that it is a storm event that happens once every 100 years. It's a statistical analysis that FEMA has come up with, and maybe a better way of looking at it is what percentage is the likelihood of that storm event happening any given year. So for a 100-year storm event, there's a 1% chance that it could happen any year. So it's like winning the Powerball. Actually, it's better than winning the Powerball. Or worse than winning the Powerball, however you want to look at it. So if you go down to the 50-year storm event, now you bump up to 2% chance every year. 25-year storm event, you go to 4% chance each year, and so on and so on and so on. Next slide, please. I wanted to explain the differences between the floodplain, the floodway, and the flood fringe areas. This diagram over here, I really like it because it really shows you what you can and cannot do and where you can and cannot do it at. So we are allowed to build in the floodplain areas, but only in the fringe areas, so these side areas. All right, that floodway is within the floodplain. The floodway and the fringe areas are both within the floodplain area. I like this illustration because this guy over here, he stopped right at that floodway boundary. He did not go over it. This guy over here, he did cross that boundary. He's going to get in trouble. So if you're in your municipalities and you see somebody going inside of their, in the floodway area, tell them to knock it off. The other thing, and I'll show you the legalities behind it here on the next slide, but the base flood elevation, that's depicted on your FEMA maps. when you have people developing in the floodway and they put in their hydraulic and hydrologic analyses saying how much they're impacting that base flood elevation, once they reach 1 foot above that base flood elevation, you're no longer allowed to develop in this fringe area, okay? Next slide. All right, so these are the regulations that we constantly have to deal with when we're talking about flooding and streams and everything like that. It all starts at the federal level. The Clean Water Act in 1972, that's where everything really stems from. And this really changes. It fluctuates from president to president. You know, depending who's in office, it can make it harder, they can make it, you know, less strict. More strict, so it's constantly changing, and you have to keep up with it. Getting back to what Dr. Weitzel was talking about and the money that is involved with these wetlands. You know, the Corps of Engineers is charged with protecting our navigable waterways, and the whole short history of that has to do with our commerce traveling, you know, down the Allegheny and then into the Ohio and then down the Mississippi and, you know, trading fur and all that, you know, back in the day. So the federal government years ago said, hey, Corps of Engineers, you're in charge of tracking our waterways. Well, they figured out that, hey, well, we got to take care of our wetlands too that are associated with our waterways, because our, you know, beaver pelts and whatever, you know, fish and all that, you know, they depend on those wetlands, just like Dr. Weitzel was talking about earlier. So the Corps of Engineers, they're responsible for managing and regulating our navigable waterways and wetlands. I'll show you this one here in a little bit. Down at the state level, we have our chapters 102, 105, and 106. That's what we primarily deal with when we're talking about streams, flooding, wetlands, all that kind of stuff. 102 is your post-construction stormwater management chapter under the state code. Any land developer has to follow the regulations in this chapter, like your detention ponds and release rates and all that stuff. The dam safety and waterway management, the chapter 105, that's if you're crossing streams, impacting wetlands, and so on. And 106 is floodplain management. And of course, down here, we have your municipal ordinances, which municipalities know full and well about. You know, the takeaway here is that the municipalities and the state laws, they can be more strict than their superior governments, but they cannot have a lower standard of the regulations. So as long as you meet the regulation, you can make your ordinances as strict as you want, but you have to meet the state and the federals, and the state have to meet the feds, and so on. All right, next slide. So this is that Title 44 CFR. This is where our floodplain ordinance comes from, is from this title here. I don't think a whole lot of people know about this particular paragraph, and I just wanted to show it to you in case the municipalities didn't know about it. The key takeaway here is this bottom couple of lines here, and really this section has to do with areas along a stream that do not have a FEMA delineated floodway. So when there's not a FEMA delineated floodway, we assume that 50 feet from top of bank is the floodway. And Breakneck Creek has that. And I think the floodway stops at Myoma Road, and everything upstream from there has no floodway at all delineated. So, so we assume it's 50 feet from top of bank. But what this does, it says, you know, combined with all other existing and anticipated development, will not increase the water surface elevation of the base flood more than 1 foot at any point within the community. So in layman's terms, municipalities have to track where that base flood elevation is fluctuating at, and they put this responsibility on the municipalities. And once anywhere at all in that municipality, that base flood elevation goes above 1 foot of what FEMA has listed it as, no more development is allowed in the floodway fringe area at all in the whole community, okay? Just wanted to make you aware of that that law, just so no one's fingers get caught. And I wanted to also mention something that Adams Township has done to kind of alleviate this. They passed an ordinance that just said, well, no more building in the floodplain at all. You know, now they don't have to keep an engineer to monitor this. And really, to monitor that, you have to have an engineer build a whole hydrologic model for your whole community, and then maintain that and update it every time there's a land development in the fringe area. So they've just done away with all that and just said, well, no one's building anymore in the floodplain with the stroke of a pen. Didn't cost a penny. So just wanted to throw that out there. Next slide, please. All right, this is our project area. This is Breakneck Creek, located between Callery and Mars Boroughs in Adams Township. This is Mars-Evans City Road here on the east. This is the B&O Railroad on the west. This is Breakneck Creek down the middle, and it does flow from south to north. So it might look a little confusing sometimes when you're looking at maps. We always think that water moves down the page. So this is the FEMA delineated floodway up here, this red hash mark. You know, so this is about 400 feet wide is what FEMA decided. And then they just stopped it. So now we're looking at, you know, 50 feet from top of bank on each side. So we went from 400 feet down to 100 feet where nobody is really allowed to develop. And you can obviously tell by this picture, we've got fill on this side, we've got fill on this side. And in some places, this is less than 100 feet wide. These are your base flood elevations, you know, so if the hydrologic analysis comes back that says this is above 976 feet, then no more developing in the fringe area in Adams Township. But they don't have to worry about that because the ordinance says no more building in the floodplain period. Next slide. All right, so the MS4 program, and I don't want to get too deep into this. I want to get to the pictures. Yeah, I'm just going to skip through this. So next slide. All right, so the MS4 program is based on really two things: urbanization from census data, and then impaired streams that are listed by the state of Pennsylvania DEP. Next. So in 2000, we did a census, and this is the urbanization map that they came up with in 2000. You can see Cranberry Township down here is almost, you know, 95% full. Here's Adams Township. We got, I don't know, maybe a quarter of the township full of urbanization. Then there's Zealy and Harmony boroughs up here. Slide. All right, and then 2010, they did another census, and that's depicted by that purple hash mark. You can see Cranberry figured out how to squeeze a little bit more in there. They're almost completely full. Adams Township almost doubled, you know, pretty impressive. And it seems to follow roadways now. So 228 is the big one in Adams Township. You can see where that urbanization took place. Another one that we're seeing is Mars-Evans City Road, and it really connects Callery and Mars Borough in that corridor. And that's where Breakneck Creek is. Next. The other thing that can really throw you into an MS4 program are impaired streams. This is a listing of the impaired streams from the DEP. And you can tell Breakneck Creek right here, it is listed as an impaired stream from its headwaters all the way to its confluence. It's one of the few streams in Butler County that the whole stream from head to tail is listed as impaired. Another one here is, I believe this is Yellow Creek here, and that runs through Lancaster County. Slide. So I like this slide because it really shows all the subwatersheds of the Connequenessing Creek, really. And you can see Breakneck Creek, and Breakneck Creek is unique in that it passes through 11 different municipalities. I think the only other creek that passes through more municipalities in Butler County is the Connequenessing. So just about every one of these municipalities, and I think every single one of these municipalities is an MS4 community. But I also wanted to hit on what Dr. Weitzel was talking about as far as the stream ordering process. You know, the numbers where it started off with like the fingers and starts at 1 and then it goes to 2 and then 3. You these stream restoration projects are really only good for order streams 1 to 3. And that's what we see in these higher reaches of the watershed. So a stream restoration project is not a viable MS4 project for larger order streams like the Connoquenessing. All right, slide. So this is a list of all the municipalities in Butler County that are listed as MS4 communities. The ones in green currently have a permit. I think we represent almost half of them. The ones in red do have a waiver right now, and good on you. I guess you got a first round bye. So after the next census, I guess hold on to your seats because it might be coming. All right, slide please. Let's skip through this. This is just a, go ahead again, next. That was just a video showing how we get to where we are with Breakneck Creek, and the long and short of that video was, going back to the 1800s, and when we clear cut everything and the farm fields were a big thing. A lot of the erosion coming off the farm fields would find these low-lying floodplain areas with the slower velocities. The sediment would drop out, giving you something like this. And this is really exactly what we see on Breakneck Creek here with 4 or 5 foot tall stream banks. And this is really what we're shooting for, is reconnection to that floodplain. Next. All right, so when you're doing a stream restoration project for the MS4, you got to meet some minimum criteria. I'm not going to get into those next. But as Dr. Weitzel said, that stream restorations, floodplains, wetlands, they have a lot of a different potential. And the nice thing about stream restoration projects as a BMP is that they're multifaceted. So you're not just helping out the ecology of it. You can use it for stormwater management, nutrient reduction rates, erosion control, which cuts down on your sedimentation, and you are improving the habitat. Go ahead and hit the next slide. This is an example. It's a time-lapse video of a stream restoration out in Lancaster, PA, on Big Spring Run that another company had done, and I guess their camera was starting to get wet. But you'll notice that the water does come up relatively quickly, I might add, and then it does flow over into the floodplain areas, and then it recedes, and that's that hydrograph, thing that Dr. Weitzel showed towards the end of his presentation. Slide. So that's the same project, the before and the after. This is really almost exactly what we see on Breakneck Creek. Really high, really silty banks, lots of erosion potential, as you can see by the massive chunks of earth that end up in the bank. Slide. So this is our project. This is the Adams Township Stream Restoration Project. We are doing about 4,700 linear feet. And we're estimating that about 200,000 pounds of sediment are going to be removed per year. I don't really have the time to talk about how we came to that conclusion, but it's part of our pollution reduction plan as part of the MS4 program. I would like to draw your attention to this area in here, the USGS map. And you can just see by you looking at the contours that the whole Breakneck Creek region between Mars Evans City Road here on the east and then the B&O Railroad on the west, this whole area is an old floodplain. And that's what the creek was supposed to spread out on and slow its velocities down. And over time, with that heavy agricultural use in the 1800s, early 1900s, that whole floodplain has filled in with what we call legacy sediment now. Next. And that's, all right, next. All right, so we do have some wetlands here. The important thing I want to point out here is our wetlands are shown in these hash marks. but they don't necessarily go right up to the stream bank, you know, and like Dr. Weitzel was talking about, we want that connectivity, and we don't have that because we've got 4 or 5 foot tall banks, and that groundwater is dropping out far before it ever reaches the top of those banks. So part of our job is to reconnect that. We also have a lot of invasive species on the site, not a whole lot of native plants. This is all reed canary grass in here. Doesn't offer a whole lot of habitat improvement, and it loves disturbed earth. You know, any wet disturbed earth, it loves it. So part of our challenge is mitigating how to keep that stuff out of our new site. Slide. All right, next. I think we hit on this pretty good. I think we beat that horse. Go ahead and hit the next button for me. This is just showing, you know, that the nitrates, phosphates, you know, sediment, you know, as they go through that buffer area, they decrease in concentration. So by the time it reaches the channel, the concentrations are minimal, and that's the whole idea behind the riparian buffers in the wetlands. Slide. All right, so the bank erosion potential of our site. We use what we call the Bank Erosion Hazard Index here, and it's broken down into 5 columns, and really I just like this because it has pictures on it. I'm like a 3rd grade reading level, I guess, so this first column here, this is your bank height versus your bank full depth. So the bank full depth is what Dr. Weitzel was talking about, that comes up over the banks maybe once a year. The DEP says, you know, 1 to 3 years, you know, so we average that to be like the 1.25 year storm event. So I think there's like an 80% chance that storm event could hit every single year. So odds are you're going to get hit with that storm event every year. And I think it's like 1.03 inches in an hour is what that storm event would equate to. So bank height versus bank full depth, yep, we got that. We've got these really tall banks, and the bank full depth is kind of like in the middle maybe. This is our picture of one of the banks up there, and it's pretty typical across the whole rest of the stream. The next one is the bank angle. We do have some undercutting, but we have a lot of vertical walls as well. The next one is your root density. As you can see up here, we don't have a whole lot of deep roots from trees. It's mostly herbaceous vegetation growing up there. The next one is your soil stratification. We do have some soil stratification here, but it's not as bad as this. So, and then the last one is your particle size. We have a lot of like fine particle sediments and clays and stuff like that, and some sand, but we don't have any cobble. We don't have any rock. There's like absolutely zero rock inside of the bank as well. It's mostly in the bed. You do have some shale in the bed, but there's nothing in the banks. Slide. All right, so that's just how I graded Breakneck Creek, you know, so we're not looking so great. The other thing that affects erosion is velocity. And this is just a diagram of how velocity contours look in a natural stream channel. So the general idea behind velocities in a channel are the farther away you get from your friction causing things like the beds and the banks, the further away you get from those, the faster your velocities are going to move. So the worst case scenario is having like a vertical wall, channelized stream with a smooth bed and smooth walls, and that's really what we have exactly right here. So we've got the perfect storm, a lot of erosion, a lot of problems, a lot of sedimentation. Next. So what do you do with that? So we started, we did test pits. We had to find out where these boundaries are, and really what we're looking for is this historic wetland that the stream used to have years and years and years ago, probably pre-colonial times. And the way we did that was digging test pits, and these little dots on this map are all the test pits that we dug. and Adams Township helped us dig a lot of those pits. Slide. And this is some of what we got. You can see the real sandy sediment material. This was so unstable, that pit was falling in on itself before it could ever take a measurement. The next slide, you can see this organic layer. Over time the sediment had come in, buried that herbaceous vegetation, then it dies off and it creates that organic layer. And then down here, this is really cool. That is the old historic wetland boundary, maybe 200 years old or older. But that's the kind of soil that the wetland plants want to grow in. When soil is wet enough for long enough, it creates an anaerobic condition, and the soil begins to turn colors and looks like this grayish blue type soil, and wetland plants thrive in that stuff, and they only grow in it. You're not going to find them in your backyard or anything like that. They have to grow in wetland conditions. So this is really what we were looking for, and we had to go in and measure the depths of all that. Go ahead, next slide. And these are some photos of our site. You can see the banks, and the erosion is so bad. It's cutting these trees and dropping them right into the creeks. And we documented our project area fairly well, but this is pretty standard for what you see between our entire project. And our project really goes from the bottom of this picture up to about here is where our outlet is going to be. Next. I just wanted to touch real quick on inside, outside of bends. The water velocity moves faster on the outsides of your bends and slower on the insides of your bends. So we have our cut banks on the outside and our point bars on the inside where the sediment deposit's at. That bank full elevation that I was talking about before is about right here in this picture. So if you drew a straight line right across, that would be the elevation that we would need to cut that berm down to in order to reestablish, what the DEP is telling us is the old floodplain boundary, or what's gonna come up over those banks every 1 to 3 years, or that 1.25 year storm event. Next. Again, you can see the characteristics and the erosion potential of this creek. Massive chunks of earth falling off, and we get so many frequent storm events now that even this vegetation doesn't stand a chance at reestablishing itself. It just washes right downstream again and deposits itself somewhere else. So naturally, this stream could find its way back to its natural levels. And really that's what we're trying to give it a hand doing. We're going to come in and excavate a lot of this soil out of here to kind of give it that jump start that it needs. Next. All right, so we're going to get into a little bit more of the engineering of the project so far. Our watershed, this blue dot up here, this is where our discharge point is for our project. So all the water running into that point is about 20.7 square miles, or a little over 13,000 acres. Our flow rates are down here. This is what we use to build our hydrologic models. You can see our 1.25 year storm event. That's the event that we're going to use to say that once a year the water is going to reach this height. Next. All right, so again, I like pretty pictures, but these are digital elevation models, or DEMs is what we call them. It's a nice way of illustrating what the ground actually looks like. This image here on the left, this is taken from what we call LiDAR data. It's a big laser scanner that scans the face of the earth. And over here is our current proposal for grading of our project site. It's not complete. When it's all said and done, you'll actually be able to see the stream bed just like this over here, but we don't have the grading quite there yet. But you can see where this particular landowner filled in over here, and then the Mars Evans City self-storage is over on this side. But I want you to notice that we are sloping. You know, this is higher up, and then the water flows from south to north. Yeah, next. So this is a cross-sectional area, and we've got these all over the project site. We might even have like 24 of them. But this is what we use to build our hydraulic analysis for the project. So for this particular cross-section, it's located up here, and this is really where we're discharging and coming out of our project site and into an adjacent landowner who we do not have an easement with. But with this cross-section, you can see the amount of fill or sediment that we're going to have to cut out of there and take out of there and truck out of there, you know, and this potentially can be very expensive, and we're trying to, you know, find ways to mitigate some of that, and we're working with Chatham with some of that as well. So if anybody needs topsoil for your yard, you know, give me a call. This is a little diagram I just made up because, like I said, we don't have it quite done yet, but I wanted to show you some of the effects that this is going to have. Hit the slide button for me, please. All right, so as the storm events come up, the water level in our discharge, I'll just say weir for this moment, it's going to rise, but it's also going to back up a little bit. You know, if you hit the button again, please. The larger the storm event, the more the water is going to back up that basin. Next. And so on, you know. So water finds its own level, and this weir here is really our control point. That is what's going to depict how much water is being stored back here. And I think I did some rough calcs and figured that this whole project area has over 51 million gallons worth of capacity. So it can store a lot of water. You know, running a quick Manning's equation with this, that'll tell you how much flow is actually coming out of that and what's actually going downstream. So, next. All right, so this is our first go-around with our H&H study using the HEC-RAS modeling. So this is the existing conditions right now. You can see the very steep channels, and this is our 1.25 year storm event elevation. So it's like right in the middle of the channel. So once a year, you're getting that bad erosion potential right there. Over here, it's showing that it's coming up over the banks and doing what we want it to do. So this shows that our plan at least works, and we're moving in the right direction. Next slide, please. All right, and so if you're a municipality and you're thinking about doing a stream restoration project, there are a few things I want to mention to you. For planning purposes, if you're trying to get easements with private landowners, do not get easements that look like this, you know, that follow the contours and the oxbow bends of the streams. Get easements that are more squared off so that the water can go on each side and flood out. So streams are windy, twisty, turny. Floodways are more, you know, squared off, okay? And then field investigations, wetlands, your soils, if you got to do any of that. All that's kind of seasonal. I don't really like doing wetland delineations in the wintertime. The vegetation isn't growing and you're going to miss stuff. So seasonal things do play in your timeline, and of course surveyors, you know, the weather can affect them. And then down here, you know, and I don't know, Roy, if you want to comment on that, you can, but that's just a general guideline as far as like riparian buffer widths. It's just a generalized recommendation. That's all. But like what Dr. Weitzel said, that riparian buffers really need to be longer. I think for the MS4 program, in order to get credit, you have to have a minimum of 35 feet. And that's just a number that they use to get credit under the program. But as we learned earlier, that it really needs to be wider than that to really have an ecological effect. So next slide, please. Okay. All right. Well.